welcome to episode number 12 of CS350 Online. I'm your host, as always, Leslie Eisted, and on today's episode, we're going to start a new topic, and that is the topic of virtual memory. But first, it's time for the OS of the day. So today's OS is one that many of you may be familiar with, and that is BSD. Now, what's interesting about BSD is that it didn't originally start as its own operating system. It was developed originally in 1978 at Berkeley. BSD, after all, does stand for Berkeley Software Distribution, and this was released for the DEC PDP-11. Now, what this software distribution was an extension to Unix version 6, the source code of which I have actually posted on Piazza. So if you're curious to know what Unix looked like back then, the complete source code you can actually find linked off Piazza. So this extension was primarily written in Pascal, which is a language that is quite similar to C. I want to say a little bit easier, a little bit simpler. And they developed a bunch of educational software. They had an editor. They offered a new shell, some new commands, and a game. And that was BSD-1. And then in 2BSD, the second one, they also included the C shell, not to be confused with that thing from CS136. But they also included VI. So VI goes back a very, very long time. 3BSD is where it actually becomes its own operating system. And before it was released, there was a few names that were going around that they were trying to decide upon. One of those names was VM Unix, because one of the names that they were, or one of the features that they really wanted to emphasize with this latest version of BSD was an implementation of virtual memory specific for the VAX hardware that they were running on. VAX is DEC, by the way. So amongst other things, they offered a number of other features. So many features that DARPA actually funded the creation of the third BSD. And it's the first Unix that had internet protocol stacks and sockets to make networking a lot more simple. Obviously, this is what the DARPA part was really excited about. So what's interesting about BSD, of course, is that it's obviously still around, and there are many, many variants of BSD that are used even today. So there's things like FreeBSD, NetBSD, but there's also, of course, SunOS and Solaris were actually based off of a BSD distribution. And if you're sitting in front of a Mac, then you also have a variant of BSD. If we go back to that little Unix chart I had here a few days ago, you've got Unix up at the top, and then right around 78, that's where you see BSD 1 and 2 branching off, then BSD 3, and then you see here that BSD forks into, it's got its own line, and you've got NetBSD and OpenBSD and FreeBSD, but then you've also got NextStep branching off of BSD, and from NextStep it goes to macOS X server to macOS X, which is what is sitting in front of you today if you're sitting with a Mac. So BSD is quite influential these days, and of course they also have a cool little mascot, unlike some operating systems. All right. So just a couple things that I want to mention before we get started into today's new topic. The first of which is that if you're looking for guides for assignment A2A and A2B, instead of having them as separate episodes, I've decided to combine them all into a singular episode, and that's episode 11, which is of course going to be on Twitch for about 12 more days, and then we'll be on YouTube until forever. The other thing I want to mention is that we will be getting your processes quiz up on Learn in the next few days. I apologize for the delay. There was an emergency in my family, and it's been an interesting week, we'll say that much. But I will get that process quiz up for you as soon as I can. All right then. So I'm going to switch over here to notepad, whatever this thing is called. OneNote, I guess. And I want to start talking to you about this concept of virtual memory. So one of the things that we've kind of glossed over in the last, 11 lectures is, what is an address space? How does the operating system abstract memory for the user programs? Now, you've got one concept of an address space that's been given to you by CS136. We're actually going to simplify it here for this course, but let's actually just draw a little address space out. So we always see it drawn as a lovely rectangle. And so in the address space, we have code, and then we've got data. And then at the end of the address space, this is where we put our stack. So that's an address space as we are familiar with it. And this address space, when you load a program, what you need to do some real good straight lines. So if this is RAM, then what we want to do is when we load a program, part of the operating system's job is to find space in physical RAM to actually load that address space. That is, find a chunk of memory that fits the address space and assign it to that particular process. So if this is our RAM here, there we go. Then what I need to do is I need to find a chunk and assign it to that process. Okay. Now, one of the things that you should have taken away from the last module of the course on processes is that we really care about the isolation of processes. We don't want one process to be able to influence another process directly. We want them to be isolated such that if I buy 30 IFV tanks, it doesn't actually go out and spend real money. So let's think about this topic of isolation as we look at how address spaces are implemented. Now let's suppose that the operating system, when it assigned us a chunk of physical memory, it actually assigned us a real physical chunk of memory. And so let's say this went from address 1000 to, let's say, that there. Okay. So if this is the address range that we are given for our actual process, and these are actual real physical addresses, there's a bit of a problem with that, actually. The problem is that by knowing exactly where in physical memory I live, I know where I don't live. I know that I don't live here. And I know that I don't live here. Which means that other programs and potentially the operating system live in these regions where I don't live. And since I know where I don't live, and therefore other things may live, that implies that I could go looking and see what's in everybody else's address space. But if I can go looking and see what is in everybody else's address space, then I haven't kept my processes very isolated, now have I? So this here does not make any sense at all. Let's look at a little sample program. So I'm going to switch over here to a terminal. I'm actually going to open a few of these here in a minute. I'm going to show you a program I wrote. It's very boring. But it's a simple program, and all that it does is it creates a global variable, it creates a stack variable, and a rather large heap variable. Fairly straightforward. And then it's going to print the address of main. It's going to, the function that is, and that should be an address in the code segment of our address space. It's going to print the address of our global variable, it's going to print the address of our heap variable, and it's going to print the address of something on the stack. And then the last thing that this little program does is it waits for user input so that the program doesn't terminate right away. Simple program. So now what I'd like to do is we're going to open up a few of these. So let's just do that. We'll open another one up here. Don't worry, there's a reason why I'm going to open like 3 of these up. It all makes sense in a second. So we're going to run it here. And as you can see, in this single execution of it, I have printed out the address of main, which is in my code segment, the address of my global variable, an address of my heap variable, and the address of my stack variable. Great. Let's open another copy. Okay, there we go. And another copy. All right. Now here's what's interesting. It looks like when we think of address spaces, we think of them as being laid out like this. Code, data, some space for growth, and then the stack. But if you look at the 3 instances of this process that are running, and you look at the addresses for their code, their data, and their stack, it almost looks like these 3 address spaces are overlapping each other. It looks kind of like I've got code 1 here, and then I've got code 2 here, and I've got code 3 here, and then data 1, data 2, data 3, and then 3 separate stacks. That's what it looks like. It looks like these 3 address spaces overlap. And I want to tell you, they don't overlap at all. In fact, there's not any kind of overlap between these address spaces whatsoever. Because these addresses that you are seeing here, the address of main, the address of our global variable, the address of our heap variable, and the address of the stack, all of those addresses are fake. They're not real addresses. They are virtual abstracted addresses. And in fact, every program that you've ever written and every run of the debugger you've ever written, every address you've ever worked with in your experience would have been a fake address. When you have a branch instruction and you say branch equal and then you give it an address, that address that you're asking that assembly instruction to branch to is also fake. All instructions, all addresses here are living at fake virtual addresses. And it's these virtual addresses that are actually going to give us the isolation between processes. All right, so let's close off these programs here. I have them actually consuming a fair bit of memory. All right. It's always good to have your slides open in advance. Unless you're me, apparently. And you don't have your slides open in advance. Let's see here. There. All right. So what is this virtual memory then? If we have all of these fake addresses. Well, the reason why we're using fake addresses is because we want to abstract the user programs from actual hardware. We don't want them to know where in physical memory they actually live, because by knowing where they live, they know where they don't live, which means they can go exploring and actually find data from other processes. And we don't want that to happen. We want each process to think it's the king of the world and that it's the only process in memory and therefore it owns all of memory. And if a process can think that it owns 100% of memory, then it doesn't believe that there's other processes lying around, and so there's no point in searching around because you can't search outside of this virtual address range. That actually raises some interesting questions though, because if you're going to have fake addresses being used for everything from variable addresses to the program counter, then how does the CPU and the address controller actually do anything if every address it ever sees is fake? And the answer, of course, is that we're going to actually have to be able to translate in hardware or in software from a fake address to a real address so that the code can actually be run, so that memory can actually be accessed. So that's what this topic is all about, this module of the course. We're going to look at several different mechanisms for implementing virtual memory, and we'll discuss kind of the pros and cons of each of those particular methods. While we're talking about pros and cons for each of these different methods for implementing virtual memory, there's three things I'd like you to keep in mind. That is, our goals of virtual memory are transparency. That is, the process or program that's running should never be aware that it's using a virtual address. It should believe that every address is the real thing, even if it's not. We also want our virtual memory implementation to offer protection, that is, isolation from other processes and from the kernel. And the most important piece is efficiency. We want our implementation of virtual memory to be efficient in terms of time and space. Because if we have to translate each and every single address we receive, well, each instruction is going to be a minimum of one translation, but some could be 2 or 3 translations. So we really need this to be very, very quick. So then, let's look at some things with virtual memory. So first off, we're going to use in these slides an example where our physical addresses use 18 bits. And if your physical addresses use 18 bits, then you have 2 to the power of 18 bytes of physical memory. So in these slides, that equates to us having 256 kilobytes of RAM, which is exactly how much RAM my very first computer had. And if you're wondering, what did 256 kilobytes of RAM look like? It was a board about this big. And the board was actually so big that there wasn't actually room inside the computer to fit it. So it actually kind of hung out the back. It had this weird piece that let it hang out the back. This is huge. And if you're wondering who made this monstrosity, it was from Quad RAM. I'm not sure they're around anymore. So in general then, if you have P bits for physical memory, then that gives you an addressable P, 2 to the power of P bytes. One thing to keep in mind about memory and addresses is that we don't do bit-based addressing. We do byte-based addressing. So keep that in mind for this module and in general. Now, our OS 161 running on our MIPS simulator, SYS161, uses 32-bit physical addresses, which gives us access to 4 gigabytes of RAM. But if you're sitting in front of a modern computer, anything, about 2003 or beyond, maybe even a little earlier than that, then, well, what you've got is more than 4 gigs of RAM, which means that we are using more than 32 bits to address physical memory. Now, in a lot of modern systems, they're using 48 bits to address physical memory. And if you're sitting there thinking, why not 64 bits? Well, if you use 48 bits to access physical memory, then you actually have access not to just gigabytes, but you have access to 256 terabytes. And I'm going to assume that none of you have 256 terabytes of RAM, because if you do, I'm coming for your computer. But you can see how we don't really need more than 48 at the moment. And I know how there's this supposed famous line where Bill Gates supposedly said no one will ever need more than 64 kilobytes of memory. To be honest, I actually tried to validate that claim, and I was not able to find any recorded proof that he actually said that. So I'm not going to say he said that. And I could sit here and say we'll never need more than 256 terabytes of RAM, but I'm sure we will. Now, if we had access, if we used 64 bits to address our physical memory, that would give us 18.4 exabytes of RAM, which is enough to drool over. That's certainly true. Now, an interesting thing I want to point out is just because you are using 48 bits to address your physical memory doesn't actually mean that you have to have 256 terabytes of RAM in your computer. Because obviously none of you sitting at home or in your basement or outside, or maybe you're the last person in Icon Tower, none of you have a computer with 256 terabytes of memory. Maybe the computer in the basement of MC has that much. I'm not actually certain. But we still used 48 bits to address physical memory. The thing I want to point out is that it's entirely possible that the amount of actual memory in your computer is less than what your system can technically address. And this is something that the BIOS of your computer is the basic input-output system that kind of controls the boot mechanism of your computer. The BIOS is aware of how much memory you have. The system is aware of how much actual memory you have. And when the operating system boots, it is also going to be aware of how much RAM is actually in the system so that you can make sure that we are not actually trying to address beyond physical memory. Now, it's interesting on the flip side of this is that it's possible that you have more memory installed in your computer than you can physically address as well. And this is less common, but right at that period of time where we were switching from using 32-bit CPUs to 64-bit CPUs, this actually did happen. People would, not realizing that you needed a 64-bit copy of your operating system, people would go out and buy a 32-bit for a 64-bit computer. And it will work because the instructions were generally at that time backwards compatible. And so you would buy, a computer, you'd put like 6 gigs of RAM in it, which is more than would be addressable on a 32-bit system. And then what would end up happening is the operating system, because it was only 32-bit, even though you had 6 gigs of RAM, the operating system could actually only access the first 4 gigs of it. So both are true. It's possible that you have more memory installed that you can physically access, and it's also possible to have less memory than you can physically access. And this is going to be kept track of through the system and through the operating system. All right. Now, our virtual addresses, these are our artificial addresses that everything is going to use. They are going to be V bits long, which means we can have a maximum addressable virtual memory of 2 to the power of V. For these slides, we're going to use 16-bit virtual addresses, which means we can access 64 kilobytes of memory through our virtual address space. Now, you will note that the number of bits used for virtual memory does not have to equal the number of bits used for physical memory. Virtual memory can use more bits, but it can also use fewer bits. Really depends on the system and the OS that you are using. MIPS, by the way, uses virtual addresses that are 32 bits. All right. So I've already mentioned it, but just to review very briefly, for a user program, everything is a virtual address. Everything. Program counter, stack counter, return address, variables, pointers, jumps, branches, go-tos, they are all virtual addresses. And because they are all virtual addresses and every virtual address range starts at 0 and goes to the maximum value, each process is going to believe that it owns 100% of memory, and it's not even going to be aware of the address spaces of other processes because this process believes it owns all of memory. So it's virtual memory that kind of seals the deal with process isolation. So the next thing that we have to talk about, and this is where the focus on this module is how do you actually perform the translations? How do you do this efficiently and using as little memory, extra memory as possible? So what we've got here is we're going to use two processes as examples. I've got process A and process B. And process A uses 28 kilobytes of memory for its address space. And process B uses 48 kilobytes of memory for its address space. Now you will note the maximum virtual memory size is 64 kilobytes. When you allocate virtual memory for a process, we don't need to allocate all 64 kilobytes. We only need to allocate the exact amount of memory that we actually are going to need and use. So even though process A and B could both have virtual address spaces that are 64 kilobytes, we're actually going to allocate less space to them because they don't need that much. Now what we're going to do then, please ignore the label in the middle of physical memory. What we're going to do is we are going to find ways of mapping these virtual address ranges into the physical address ranges. And the first method is exactly that. It's pretty much a direct mapping from the virtual address range to a physical address range. And this mapping for this example is called dynamic relocation. Dynamic relocation is the easiest of all of these different virtual memory implementations that we're going to talk about. But in order to make this translation here work, and I'll talk about this in just a sec, we're going to need one more piece. So dynamic relocation is going to take this virtual address range here from 0 to 6FFF, and we are going to map it to a physical block of memory. And in this case, process A gets mapped over here to physical address 24,000. And so this mapping, when we're doing this translation, to go from a virtual address to a physical address, we simply add the offset, which is the position in physical memory where that address space starts. And then to go from physical back to virtual, you're going to subtract that offset. All right. So, who does this translation? Somebody's got to translate it. Somebody's got to do this addition. Somebody's got to do this subtraction. And it's very tempting to believe that this is the operating system that's going to do it. But think with me for a minute. If the only way you can make the operating system do anything is by firing an exception, and we want the operating system to actually perform these address translations, then you're saying that at least once for every instruction of your entire program, we have to fire an exception. I think that would actually make your program probably 1,000 times slower than it already is, which means that we shouldn't be using the operating system to actually do the translations. What we're going to do instead is we're going to use hardware to do the address translations. And this piece of hardware you probably might have heard of in CS350, although I'm sure everybody has forgotten about it because that was probably a long time ago. It's called the MMU, or Memory Management Unit. And the goal of the Memory Management Unit is it translates every virtual address to a physical address so that the CPU and the address controller from RAM can actually use it. So that's pretty cool. And if you're wondering, where does the MMU live in your computer? Your MMU is actually part of the CPU. All right, so how does the MMU actually perform the address translation for dynamic relocation then? Well, we've already talked about how the mapping from virtual to physical addresses is simple as adding and subtracting this offset piece. Well, we also need one more thing. The other thing that we're going to need is we need to know exactly how big the address space is. Not how big virtual memory is, but how much memory the process actually is using. So we're going to actually, for each process, store two integer values. The first integer value is going to be the offset, or the relocation. And that is, where in physical memory does this address space actually start? We also are going to store the limit, and the limit is the length of that allocation. Now, we're going to keep both of these integers for each process, and we're actually going to store that as part of the address space. And then whichever process is running, the MMU is actually going to keep its own copy of the relocation and limit values for that process in special registers on board the MMU. And then when the MMU receives a virtual address, the first thing it's going to do is check to see if it's a valid virtual address for this process. And why does it have to check? Because people write beyond the end of arrays all the time, and we don't want to translate an address that doesn't work. So what we're going to do is we compare the virtual address to the limit. If the virtual address is less than the limit, then we know that this virtual address is valid and it's inside the address space. And if it's valid and inside the address space, then we simply perform the translation by adding the virtual address to the contents of our relocation register, and we're done. And if, however, the virtual address is greater than or equal to the limit, then it is not in the address space for this process, and therefore it is not valid, and so the MMU throws an exception, and that exception, of course, would be handled by the operating system. Okay. Doesn't seem so bad, does it? It actually seems like this is a really good mechanism. If we think about this method in terms of its efficiency in time and space, for each of our processes, we only need to store 2 extra integers. And if you look at how much physical memory we actually have available to us today, storing 2 extra integers per process doesn't actually seem like much. So in terms of space, this is really reasonable. Now, in terms of time, how long does it take to actually compute the translation? It's also very efficient because all we're doing is adding and subtracting. Okay. So why do we need to have an entire 6 lectures, 6 episodes dedicated to this topic? Because as easy as dynamic relocation is, it's also really bad. And the reason why it's really bad, we'll come back to doing some sample problems here in a minute. The reason why this is so bad is because address spaces don't look like that. We have assumed in this example that our address spaces all got the code, the data, and the stack segment tightly squashed together. And you and I both know that's not what it looks like, because we put lots of space between the stack and the heap so that they have an opportunity to grow. So our address space doesn't actually look like this. Address spaces actually look like this, where you've got the code segment, the data segment, and then the heaps or the stack segment really far away. If we were to use this real address space here with dynamic relocation, every single process would have a 2 GB address space, every single one, because dynamic relocation requires a contiguous allocation, one contiguous allocation. And with a real layout from an address space, that would be 2 GB for every process because of all the extra white space in between. All right. So what ends up happening, by the way, is there's 2 side effects. Dynamic relocation, if we use real address spaces, is going to restrict how many processes that you can actually run at the same time. So it's going to be a restriction on the degree of multiprocessing. The other problem is, of course, that if each process uses a 2 GB address space, well, you're only going to be able to run a very small number of programs. You're going to run out of RAM really quickly. If we, however, use the address spaces layout as suggested on slide 7, the problem you run up with here is that you get external fragmentation. That's the problem. Bring up notebook here. External fragmentation is the problem where as you are allocating, that's a really bad rectangle. As you are allocating memory if each chunk is a different size. So let's say this is A, this is B, this is C, and D. And let's say E and F are technically free. And let's say we want to load a new program, and technically E plus F would fit the program, but because they're not contiguous, we can't actually allocate them. So this is external fragmentation. And then the problem with the other problem with using a real address space, aside from reducing our degree of multiprocessing, the problem is we end up with internal fragmentation because we've got large gigabytes of memory inside the address space, which we're not using and nobody else can use. So dynamic relocation is really nice in the sense of it's really simple and all of those things, but I'll be honest with you, it's also not so great in terms of fragmentation. Okay, so let's do some samples. So here we've got two processes. We've got a limit register and a relocation register. And I want to know whether these work out or not. So let me open up. Trying to take a window snapshot. There we go. So let's look at these. For process A, the first thing I'm going to do, remember, let's be human MMUs for a moment. Let's look at then the limit register and compare it to our virtual address. That's part one. So I compare the limit 7,000 to 1,000 to C. Oh, you know what? That's a valid address. So now I'm going to do the translation, which is as simple as adding 102C to 24,000. So you should get for this one 2502C. It's not bad, right? Now I look at the next address, which was 8,000. 8,000 is bigger than 7,000, so this address is not valid. When you get an address that's not valid, you write exception, spelled really badly. And then the last one here, 0, is obviously less than 7,000. So the last address you should get is 24,000, like so. All right, so what about process B then? Well, for process B, we've got the same set of virtual addresses, because remember that each virtual address range is the same, so they're going from 0 to the maximum, but where they map to in physical memory is different. So two processes can actually use the same virtual address range, but that does not mean they overlap in physical memory, because their relocation and limit values will be different. So for process B here, this is less than C1000, so we can translate that, and that's going to translate to 0x1402C. 8,000 translates this time. So 8,000, you should get let's see, that's going to be an 11, 1B000. And then we've got 0, which is going to be 0x. Oops. That's a 0. There we go. That's not a 6, that's a 0. All right. Easy, right? But it doesn't work because it gives us fragmentation. Okay. So let's solve this problem. As I said, memory actually looks more like this when we have an address space. Our address space is actually going to be laid out with a code segment, a data segment, and a stack segment spread apart. Now, the problem with dynamic relocation is you're either going to have external fragmentation or internal fragmentation. And I'd like to do something to get rid of that fragmentation. So what am I going to do? Well, why not, instead of tracking just one contiguous allocation, why don't I make note of the fact that I've got 3 distinct segments of memory, and let's have contiguous allocations for each of those, because then I won't have any internal fragmentation whatsoever, because I'll only ever be allocating exactly the space that I need. Okay. And that brings us to our second implementation of virtual memory, which is known as segmentation. Now, what happens with segmentation is we need to create a method for identifying, is this virtual address a part of this segment or this other segment? But once we've done that, the address translation within each segment is just going to be dynamic relocation all over again. So let me show you an example actually here in OneNote. So, page. I should probably learn the shortcut keys, but I never do. All right. So what we're going to do is, if this is our address, and let's say our address is, well, our virtual address is 16 bits. Then what I'm going to do is I'm actually going to divide it into 2 parts. So instead of having this be the entire address, my segmentation address is now going to be composed of the segment number, and then the remainder of the address would be the segment offset. So what's going to happen is the MMU is going to know how many bits we use for the segment number. And the MMU is going to peel those bits off and say, well, which segment is this? And then the MMU is going to look up for that segment, what is the relocation and what is the limit. And then our address translation is going to be the same as dynamic relocation. It's that easy. Now, how do you determine how many bits you're going to use for the segment number? Well, how many segments do you have? It's going to be the log of the number of segments. And of course, you're going to have to take the ceiling of that because you can't have a fractional number of bits. So, if I have 1 segment in my entire address space, I need 1 bit. Well, actually, I don't need any bits. So in this case, I need no bits. But no one would ever do that. If you have 2 segments, then your segment number uses 1 bit, because you'll have segment 0 and segment 1. If your address space has 4 segments, then you need 2 bits, and you will have segment 0, 0 segment 0, 1, segment 1, 0, and segment 1, 1. Not too bad, right? All right. So let's go back and look at that slide then. Not that slide. There we go. So we're going to take some number k bits to represent our segment number. That leaves us with 2 to the power v minus k bytes for our actual segment. So using segmentation is actually going to reduce how much memory we can have in our code, our data, or our stack. But that's going to be okay because we won't actually be using that many bits for our segment numbers. There aren't really address spaces in the real world that have like 30 segments. So we don't need that many bits for the actual segment number. All right. What we're going to do then is we're going to talk about 2 different implementations of the MMU. The first implementation is where each of the segments is going to have its own relocation and limit register on the MMU. So looking at this example here, which actually shows you how we're going to map each of the segments into physical memory. So process A has 2 segments, process B has 2 segments. So we're just going to find a contiguous block of memory that fits segment 0 for A and the same for segment 1. And then we'll keep track of segment 0's limit and offset, and we'll keep track of segment 1's limit and offset. And then if process A was running, then we would have our MMU with segment 0 registers and segment 1 registers. And for each of the segments, the MMU will have a relocation and limit register. And then when we do a context switch to a thread from process B, we have to clear the MMU and give it new values for its relocation and limit registers. So with this, how address translation works, where the MMU has the relocation and limit register for each segment, we're first going to peel off the bits to figure out what segment number this is. Once the MMU figures out which segment it is, then the MMU will know which of its relocation and limit registers to use for the translation. So we've got the segment bits peeled off. The next thing we're going to do is get the segment offset, which is all of the remaining bits of the address. We compare the segment offset or address within the segment to our limit for that segment. If it's greater than or equal to the limit for the segment, then we generate the exception because it's not a valid address. And if it's less than the limit for that segment, we simply add the relocation value and we're done. So instead of doing dynamic relocation on our on the space as a whole, now we're just doing dynamic relocation on the individual segments. All right. That's method 1. Now this is not a method we actually use in practice, and the reason why we don't use this in practice is because this requires the MMU to have a very large number of registers. Registers actually take up space, and generally speaking, we want the profile of each of these components to be very, very small. So we don't want our MMU to have a lot of registers. One of the other problems too is that it would have the MMU actually dictating how the address spaces have to be implemented in the kernel of the operating system. And generally speaking, people don't like to be told what to do, so we don't want our hardware telling us what to do here. Now, something else to point out is that 2 registers per segment isn't even enough. So we haven't even scratched the surface of how many registers you would actually need for each of these segments. Because we haven't discussed the fact that some segments should be read-only. How would we mark these segments as read-only and some as not read-only? Well, we would need to use another register for that. So this is not used in practice. There are better methods to actually do this. Better method. We'll come back to the translation bit in a minute. So a method that you'll see more commonly used for segmentation in practice is the concept of a segment table. And essentially, we're going to have a table stored in memory that stores the segment number. The index of the table will be the segment number. And then for each of the entries in the segment table, we will list the limit. We will list the offset, and we can also have flags like, is this read only? When was the last time somebody used this segment? And so on and so forth. So we can have a lot more flexibility in our implementation if we use this segment table. And our MMU will remain blissfully simple because instead of having registers for each and every segment, we have a segment table length register, which tells us how many entries in the segment table are actually being used, which is interesting because that gives us the ability to have address spaces with different numbers of segments. And then our second register is simply a pointer to where that table lives, and that's it. So the segment table is a much more common way of actually seeing segmentation implemented on our MMU. The translation works the same though. The MMU is going to peel off the segment bits. If it is a valid segment number, then we will use the segment number to index the table and get our limit and offsets, and then we will simply do the addition like we did before. All right. Let's actually do some translations here. Now I'm actually going to do this in OneNote because that annotate program is a little bit irritating. So there are our addresses. And what we're going to do now is let's actually translate them. So for process A, and I'm only going to do them for process A. I would like you to try these for process B on your own. So for process A, I have two segments. Well, I have two segments for each. Because I know that I only have two segments, I know my segment number is 1 bit. And I'd like to point out that the segment number is always going to be the highest order bits of the virtual address. Okay, so I put my segment number in the highest order thing. So let's look at virtual address 0x1240. Which segment is this a part of? This is segment 0. Now for some of you, you might be confused as to why 1240 is in segment 0, but think of it this way. This address, as I have specified it here, is actually in hexadecimal. When we're talking about segment bits, we're talking about binary bits, not hexadecimal digits. This 1240 is actually that address there. And if you look at it, the highest order bit is a 0. And so that I know that my segment number is a 0. Now, what is my segment offset? My segment offset are all the remaining bits. So in the case where our segment number is 0, then my segment offset would be the same as the virtual address. So here we get 1240. Now the physical address. So in order to compute the physical address, I need to look up the relocation and limit for this segment. This is segment 0. So I see segment 0 has a limit of 2,000 and 1,240, that is less than 2,000. So this address is valid, and my relocation is 38,000. So what I'm going to do then is just add them together, and I should get 0, 3, 9, 2, 4, 0. All right, so that's the first address translated. Now let's look at the second address here, which is A0, A0. Now something to remember is that A is actually 1, 0, 1, 0. So my segment number here is going to be 1. Now how do I get the segment offset? So what you're going to do for the segment offset is you're going to set the segment bits to 0. And then whatever's left, that's your address, your segment offset. So my segment offset here is not A0, A0, but 20A0, because when I set this segment bit to 0, I'm left with 0, 0, 1, 0, which is 2. Now, this is in segment 1. Segment 1 has a limit of 5,000, so I'm going to add 20A0 to 10,000. So that should give me 0x 120A0. All right. Now let's look at the next one. The next one is 66AC. Now 6 is going to be, of course, so this is going to be in segment 0. And my offset is then just the address again, because the segment bits are already 0. And then I compare 66AC to limit 2000, and I realize it exceeds it. And so this is an exception. Yay. And then our last address here is E880. Now, E is 1110. So my segment number for the last one is 1. And so segment 1, I'm going to set that bit to 0 to leave me with 0110. And so that is actually going to be 06880, which again is going to be greater than our limit. So that is also an exception. And we're done. That's it. So I'll let you try these for process B. 2 things to note is how we actually separate the segment number from the segment offset. The other thing that I want you to notice is that even though we have the same addresses for process A and process B, and it looks like the 2 address spaces overlap, they don't in reality because they map to completely separate physical spaces. Now, if you're wondering, where does the term segmentation fault come from? Is it related to this implementation of virtual memory? And the answer is yes. What a segmentation fault means is that the address lies outside of the segment. That's exactly what a segmentation fault means. So it's been around for a long, long time. All right. So then, why do we need to have 40 some more slides left in this module? This segmentation approach actually seems that it's a really good idea. It is a good idea because for minimal extra data, we don't end up with any internal fragmentation. So let me explain that in a little more detailed. Now, instead of having 1 relocation and 1 limit value stored for an entire address space, we simply have a limit and relocation value stored for each segment. Since I know that I don't have many segments in my address space, at most maybe I'm storing 10 extra integers per process. If you've got gigabytes of RAM, you don't care about 6 extra integers or 10 extra integers per process. That is trivial. So segmentation is efficient in terms of how much memory it uses to actually implement the technique. Segmentation is also efficient in terms of how long it takes to perform the translation. We separate the bit offset from the segment number and we simply do some adding. Very, very easy. Almost as easy as dynamic relocation. Another advantage of segmentation is we never keep track of regions of the address space that we're not actually using. So there's no internal fragmentation with segmentation. But this actually suffers from external fragmentation. The problem is that each of the segments is a different length. And so all of our allocations of physical memory are going to be different lengths, which means that since each segment has to live contiguously in physical memory, we may come across the problem where we technically have enough memory, but because it's not contiguous, we can't actually create the process. That being said, segmentation has been used for many, many years. It's one of the original mechanisms that was used for virtual memory and proposed back in the 50s, although people realized very quickly it had fragmentation issues. All right. So how do you solve this issue of fragmentation? Well, what we need to do is we notice that the external fragmentation problem arises from the fact that all of our allocations have a different size. So what I need to do then is I need to make all of my allocations the same size or multiples of the same size. So what if I did this? Let's take my physical memory and let's subdivide it into a bunch of equally sized chunks we're going to call physical pages or frames. And let's, for the sake of argument, say that each of these frames is 4 kilobytes. And let's suppose that I only permit allocations that are multiples of the frames. Well, let's take it a step further, because then I could have a problem where I'm allocating 5 frames versus 6 frames, and I could still end up with fragmentation. What if I only allow allocations that are single frames in size? So I never allow contiguous blocks of frames. How would we do this with virtual memory? Well, what we need to do is, just like we've subdivided physical memory, we're going to subdivide virtual memory. And we subdivide virtual memory into equal sized pages, such that the pages and frames are the same size. And then the magic that I'm going to do is, instead of requiring a contiguous block of n pages, I'm going to say, map each individual page of virtual memory to some random frame of physical memory. So instead of our address spaces being contiguously allocated in physical memory, they will now be spread to the wind. But since each of the chunks that we asked for from physical memory are the exact same size, we have no more external fragmentation. But we can have internal fragmentation. But the question you have to ask yourself is, do you care? If each of your pages is 4 kilobytes in size, then let's say your address space only needs 1 kilobyte. You would have to give it 4 kilobytes. So 3 kilobytes is wasted. If you waste 3 kilobytes per process, well, if you have 1,000 processes, that's only 3 megabytes. If you have gigabytes of RAM, you don't care about 3 megabytes being wasted. So the internal fragmentation or internal wasted space for this paging implementation, we don't actually care about so much. It's not, in today's memory terms, it's not worth discussing. But we have solved the bigger problem of external fragmentation. However, we just made address translation really, really complicated, because now, instead of having 1 limit and 1 relocation register for the whole thing, or 1 limit and relocation registers for the individual segments, I could have millions of pages, and I'm going to need to store information about each of those pages and where they are living in physical memory, because we're not taking advantage of contiguous allocations anymore. So what does this actually look like? We have to create what's known as a page table. And our page table, this is something that gets very confusing for students each term, we notice, is that our page table doesn't contain only the entries we are using. It actually contains a page table entry for every possible page of virtual memory. What I'm saying is that if we are only using 7 of the 16 pages, our page table needs to still contain all 16 possible page entries. And what the page table contains is the index is the page number, and then for each page table entry, we keep track of which frame number this page maps to. And then we have a bit we use to keep track of whether we're actually using this page or not. Now, why do you need this valid bit? Well, this example is using an address space which is contiguously allocated. That is, there's no space between the stack and the heap and the code. But we know the reality that that isn't true, that there's space between them, which means you're going to have a little segment of pages used here, a little bit used here, and a little bit used all the way over here. So I am going to have empty pages in between pages that are in use, which is why page tables actually have to have an entry for every page regardless of whether we're using it or not. And we use the valid bit to indicate whether it's in use or not. So for our little example, we have 16 pages of virtual memory because our pages are 4 kilobytes in size. And of those 16 pages, we are using 28 kilobytes of the 64. So we are using 7 pages of the 16 possibilities. And for the second process, we are using 12 of the possible 16 pages. So I'm going to leave this here for today. I don't want to get into any math at this point in the last few minutes of today's episode. So on next week's episode, episode number 13, we're going to take a closer look at page tables. We're going to look at the math to compute how many pages of physical memory there are, how many pages of virtual memory there are. We'll also look at how you actually perform the translation to go from page to frame, and we'll look at the format of the virtual addresses so that we can understand that better. If you have not done a lot of hexadecimal math recently, I recommend that you give yourself a brief refresher on it. This is normally where I would say things like, make sure you can do this without a calculator, except you're not actually going to have any in-person exams, so use a calculator all you want. I don't care. All right, so we will see you on Tuesday of next week to learn more about the math behind our page table implementation.
Sir, is this your computer? Yeah, it's unusually thin, sir. Please open it. Is this large area the screen, sir?
Yeah?
Sir, the screen is abnormally large and unusually bright.
I know.
Not the usual computer now, is it, sir?
No, it's not.
Supervisor to station 12.
It's a showstopper. The High Note Ultra 2000 with Intel Pentium processor with MMX technology from Digital.